In this video, we're going to learn how to draw Lewis structures for covalently bonded compounds. The way that we can illustrate bonding between atoms in a molecule are quite varied. We can have our molecular formula, which is just the formulas that we've learned to write. You can have a structural formula, which we're going to talk about in just a second, a little bit more. But we can also have the ball and stick and the space filling. Ball and stick and the space filling are a little bit more accurate representations of what nature has. However, they are much harder to draw. Therefore, the structural formula is actually quite preferred by chemists because it tells us about who is bonded to whom and what the molecule might look like. Now, when drawing a Lewis structure, we use single lines to represent bonded pairs of electrons. So let's take a look at the first possible molecule we have up top, and that would be the hydrogen. And so we would connect the two hydrogen atoms with a line. That would be our H2. Down below we have water. Now these two atoms would connect and these two atoms would connect, and that would be our H2O. Off to the side we have methane. So we would see that we have four possible bonds that we can form, and here we have our good old methane. So single lines represent a pair of electrons. Now, with hydrogen, we know we can't follow the octet rule, we can only follow the duet rule. But what about in terms of the water? Well, in water, we have the oxygen surrounded by 2, 4, 6, 8 total electrons. That means it has an octet. In the methane, we have 2, 4, 6, 8. Carbon also has an octet. So it's quite important that we try to obey the octet rule when we're drawing our Lewis dot structures or our Lewis structures. So we want to have 8 valence electrons. So we saw in water and we saw in methane that they have 8 valence electrons. Well, what about something like hydrofluoric acid? HF has this Lewis structure. Now, how many electrons are surrounding that fluorine? We've got 2, 4, 6, 8. And don't forget that the total number of bonds formed is going to be based upon the number of valence electrons that the atom has. So for fluorine, we had 7 valence electrons. It can only form one bond because 8 minus 7 is 1. So how do we draw Lewis structures? Well, the steps in determining the Lewis structure for a molecule are pretty straightforward. The first thing we need to do is we need to determine who is the central atom. And the guy that's going to be the central atom is going to be the one that can form the most bonds. So the one that has the most open valencies. And remember that molecules tend to be compact so that the other atoms that are in a molecule tend to attach to the central atom. Now, once we've determined the central atom, we put it in and just draw its symbol, and then we place all the other peripheral atoms around the center. Then we draw the Lewis structure for each individual atom by placing dots around those atoms corresponding to their valence electrons. And then we can draw a line to connect the valence electrons to show that we have valence electrons coming together to form a pair. This is essentially connecting the dots. Now, the last step is we need to check for octets if possible. Remember, there are some that do not obey the octet rule, and we'll talk about those. And the last step is always to make it pretty, to redraw it, because when we're drawing these lines, it can get kind of ugly. So let's work on some example problems. Let's start off with ammonia, NH3. Now, the one that is going to be the central atom is also usually written first, but it's the one with the most open valency. In this case, nitrogen is going to go in the center, and we are going to place our peripheral atoms, the hydrogens, around the outside of the nitrogen. Now we put the valence electrons on each individual atom. Well, the hydrogens are easy because there's only one valence electron on each. On nitrogen, we have a total of 5 valence electrons. So I'm going to start putting my valence electrons around, and see that I've got my 5. Now wherever I have an open valency, that's where I'm going to connect the dots. So I'm going to connect those dots, connect those dots, connect those dots. Now I need to check to make sure that nitrogen has an octet. So we've got 2, 4, 6, 8. 8 valence electrons. Now that's really an ugly drawing. So the last possible step we need to do is we need to redraw this to make it pretty. And there we have it by the magic of video editing. We have a much prettier drawing for the Lewis structure of ammonia. Next, let's take on carbon tetrachloride. The center valency is going to be our carbon because it can form 4 bonds. We are going to place our peripheral atoms around the outside. These are the chlorines. Now we need to place our individual electrons on each of our atoms. So we have 4 for our carbons, and then we have 7 for the chlorine atoms. So here we go around putting out 7 valence electrons on each chlorine atom. Then we connect the dots, connect our open valencies. So I've got one that goes there, one that goes there, one that goes there, and one that goes there. I need to check for my octet. So carbon has 2, 4, 6, 8. What about our chlorines? Chlorines actually also have an octet. 2, 4, 6, 8. Remember, because these pairs are shared, they're not on any one atom. So both atoms feel like they have that pair. They both have access to it. And the final step is to redraw it. So by the magic of video editing, we have a new structure. Just like that. Now let's continue on and try our hand with H2S. Now, sulfur, even though it's not written first, has 2 open valencies because it has 6 valence electrons. And then the hydrogens each have 1. Now, once you've done this a while, you can start mixing the steps up like I just did, where I put all of my electrons in for my atoms while I was drawing them. And then we just connect our open valencies, check for our octet. So sulfur has 2, 4, 6, 8, and the hydrogens each have 2. And through magical video editing, we have our brand new redrawn structure for H2S. Moving on to CH2Cl2, carbon again is in the center, and then we're going to have the 4 dots around the carbon. Then we have a hydrogen and a hydrogen, with each having 1 dot, and then we have 2 chlorines, each having 7 dots. We connect our dots, and then check for our octet. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Everybody's happy. We're going to redraw it. Now you may be wondering, does it really matter where I put the chlorine, whether it goes on the bottom here, on the side here, or wherever? And the answer is no, with a but. We do try to keep them on the 4 sides of whatever element symbol's in the center if we can help it. Now let's try taking on an ion like NH4+. When we have ions, and we're drawing Lewis structures for the ions, we have to remember that ions either have added or subtracted electrons. So in terms of the ammonium ion here, we've got the nitrogen in the center and 4 hydrogens that is going to surround it. Now each hydrogen comes with 1 electron. The nitrogen comes with 5, but remember, we actually need to take 1 electron away. So if I take away an electron off of the nitrogen here, which I'll do just like that, let's put that extra nitrogen electron there. When I go to draw my dots, I don't have any extra dots. Now, nitrogen has 2, 4, 6, 8 total electrons. But because we've shown that it is an ion, we took an electron away, we need to make sure that we state that somehow. So we always finish by drawing brackets around our ion and putting the charge on the outside. So if we go ahead and redraw this, and we make it pretty, there is the ammonium ion. Now let's try tackling the hydrogen sulfide ion. Sulfur is in the center, but really there's no center because there's only 2 atoms. And sulfur comes with 6 valence electrons, and hydrogen comes with 1. Now, this time we've got a negative charge, so that means we have to add an electron. So we'll add it to one of the spots where we needed an extra pair. Go ahead and connect the dots, and then remember, we need to put brackets showing the ion charge. And finally, of course, we redraw it. And there we have the hydrogen sulfide ion. Now, everything we've done so far has been singly bonded species. But sometimes, when you're drawing these, you find that you've got every connected atom, but you still have some open valencies. That is when you're going to start consider multiple bonding, only if you have open valencies. So let's take a look at something like carbon dioxide, CO2. CO2, the carbon goes in the center. It has the 4 valence electrons on the outside, 2 oxygens around the center. Each oxygen comes with 6 valence electrons. Now, if I just make the single bonds there, you can see that I've connected the atoms. They're all connected, but carbon has got 2 extra valencies, and each oxygen has an extra valency as well. Additionally, if you take a look and count the number of electrons around the oxygen, we've got 2, 4, 6, 7. 2, 4, 6, 7. And carbon has 2, 4, 5, 6. They want to have an octet, so this is where we're going to consider multiple bonding. So perhaps if I draw a line between those two, and then maybe a line between those two. This is really ugly, so we make sure that we redraw this one. And this is what we get when it's all nice and pretty. Carbon with 2 double bonds, 1 double bond to each oxygen. Now, go back and double check the valencies. There's 2, 4, 6, 8 around the carbon, and 2, 4, 6, 8 around each oxygen. Let's also try something like nitrogen, N2. Since there's no real central molecule, we're just going to write our 2 nitrogens. Each one has 5 valence electrons. Now if I connect the 1, you can see that there are still open valencies on the nitrogen. So I can go ahead and connect those guys. And of course, that is really ugly, so we redraw it. And there we have a pretty triple bond to nitrogen. Now, one thing to remember is we're never going to go above a triple bond. There's nothing more than a triple bond. So you can have single, double, and triple bonds, but no quadruple bond or anything above that. And then, let's take a look at a final example, something like hydrocyanic acid. Carbon goes in the center. It has 4 valence electrons. The nitrogen has 5 valence electrons, and then we have a hydrogen with 1 valence electron. Now, if I connect everybody up, I can see that carbon and nitrogen both still have 2 open valencies, so I can connect those. And if I redraw it, I get hydrocyanic acid Lewis structure. Now, carbon is kind of special because it can form the most bonds covalently. It can form 4 single bonds, or just 4 bonds total. And it has the ability to catenate. Catenation is when the carbon atoms come together and form chains or rings. An example of this is C6H14 hexane, which can be drawn like this, where each carbon is singly bonded to another carbon, and on the outside you are surrounded by 3 hydrogens. But the problem is this formula, C6H14, does not have enough information to tell me that that is actually the structure I'm looking for. In fact, what about this structure? This structure also has 6 carbons and 14 hydrogens. What about this structure? These are what are known as structural isomers. Structural isomers. The only thing that's changed here is the connectivity of the chain, the carbon placement, and this affects what molecule it is. That's why you'll see when we talk about organic nomenclature that it is completely different because we have to specify positions of these branching portions. Just be aware that when we deal with organic molecules, the possibility for structural isomers exists. Now, since the octet rule is a rule, that means there must be exceptions. It's not the octet law. So, what are the exceptions to the octet rule? Well, let's start with the first one, too few electrons. We've already sort of covered this when we talked about hydrogen. It can't hold 8 electrons, so it cannot follow the octet rule. Or something like the boron in BH3. It has too few electrons, it cannot hold more than the 6 electrons it gets. Another example of not obeying the octet rule is going to be when you have an odd number of electrons, something like NO2. The odd number of electrons occurs mainly between nitrogen oxides. So when nitrogen is attached to oxygen, it can end up having too few electrons because of an odd number. So nitrogen dioxide actually has a formula that looks like this. Notice the nitrogen here ends up with 2, 4, 6, 7 total electrons. It's not a very stable molecule because nitrogen really wants to have an octet, but this is a possibility. Now, the biggest exception comes when we can expand the octet. This is when we have too many electrons. Now, the expanded octet can only occur from period 3 and below. What's so special about period 3? Well, period 3 is where we start getting d electrons. So if we take a look at the main group elements in period 3, something like phosphorus or anything below that, iodine or bromine, these things can have expanded octets because it has empty d orbitals. It can use those d orbitals to form bonds. So let's take a look at some examples. So the first example we have is PCl5. Now I'm going to work through this example and show you that indeed we have an expanded octet. Phosphorus goes in the center. It has 5 valence electrons. The chlorines go around the outside. They each come with 7 valence electrons. And now we can connect open valencies. And if I connect only the open valencies, you can see that I'm done. Phosphorus has got an octet. It's happy. But since PCl5 exists, then it must have an expanded octet. It must take on more than 8 electrons. And you can see that I've got a pair of electrons at the top of the phosphorus, and I've got 2 open valencies on each of on the chlorines. So I can actually break apart that pair to form new covalent bonds with those chlorines. And of course this is ugly, so I'm going to redraw it. And there I have PCl5. Now, each of the chlorines has got an octet, but the phosphorus holds 2, 4, 6, 8, 10 electrons. Not the octet, an expanded octet. Now let's try IF7, iodine heptafluoride. The iodine goes in the center. It has 7 valence electrons. And then I'm going to place 7 fluorines around the outside. So each fluorine comes with 7 valence electrons. So there's 2, 3, 4, 5, 6, and 7. Now if I connect just the open valencies, I'd be done. So what I'm going to end up doing is I'm going to end up having to form bonds using our paired electrons. So if the fluorine here attaches there, and then that fluorine attaches there, and then this one here, and that one there, and then that one there, and that one there. Now look, I've used up all the electrons on the iodine, and every fluorine has also got 8 electrons. This is ugly, so we redraw it. And there we have the Lewis dot structure, or the Lewis structure for iodine heptafluoride. Now let's do the sulfate ion. Remember, this is an anion, so I'm going to add 2 extra electrons. The sulfur is going to go in the center, and it has 6 valence electrons. Then we're going to put 4 oxygens around the outside. Now I'm going to connect open valencies, and when I do that, I'm out of valencies. Now, you can see that there are 2 atoms that need to be connected. So I'm going to go ahead and connect those guys using a pair that I've already used. Now, don't forget there's also an ion, so that means that I can add 2 more electrons. So I'm going to add those electrons. I'm going to add 1 electron to that, and maybe 1 electron to that one. Does it matter which ones I added to? No, it doesn't. But notice that I've still got 2 open valencies on the oxygens and 2 extra electrons on the sulfur. So I'm going to go ahead and connect those guys up. And wow, is that ugly. So what do we need to do? That's right, we need to redraw. And don't forget to put brackets and the charge around the sulfate ion. Now each oxygen atom has got 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, and the sulfur has 2, 4, 6, 8, 10, 12 electrons. So we have again another expanded octet. If you want to do some more Lewis structures or read up on Lewis theory a little bit more in depth, follow the link above to the University of California, Davis Chemistry Wiki. There's a lot of good information here, a lot more than what we cover in Chem 110, but it's some good stuff. So, thanks, and I hope you enjoyed the video.